Welcome back, calculus students. We're looking now at assignment 9, which is section 3.3, going over the rules of differentiation. I want to remind you of these four important rules that we have already established. And they are simply that the derivative of any constant will be 0. The derivative of x to the n will be n times x to the n minus 1. And we've only shown that that's true when n is a positive integer. We've also shown that the derivative of a constant times a function will be the constant times the derivative of the function. And finally, we've shown that if we're taking the derivative of the sum of two functions, that will be the sum of the derivatives. And the derivative of the difference of any two functions will be the difference of the derivatives. You should be able to understand at this point that when we put these four rules together, we can now find the derivative of any polynomial at all, and that's a big deal. For example, if we're trying to take the derivative of this polynomial that we're looking at, using the rules that we have, we can see that this derivative will equal 12x squared minus 10x plus 7. It's really quite easy to take the derivative of any polynomial at all. We note also that when we talk about a graph having a horizontal tangent, if you think about what that means, the derivative must equal 0. A lot of students often jump to the conclusion that, okay, if the derivative is 0, we have a max or a min. And I think we've already talked about this, but we only have a max or a min when the derivative changes sign. So just equaling 0 isn't enough. We've looked at graphs like that, and if I look over here in the bottom left, here's a graph where the derivative is 0, but there is no max or min. So the derivative is 0 right here, but the function is increasing, 0 increasing. The derivative is positive, 0 positive. We don't have a max. At this point in the course, you should know how to use your calculator, whether it's an Inspire or a TI-89, to take the derivative of any function and also to take the derivative of any function at a specific point. Both the manual for the Inspire and the TI-89 are found on the NMH web page under the math folder. So that's easy enough to do. So now let's talk about this. If we're talking about the derivative of the product of two functions, at this point, most students will guess that the derivative of a product is equal to the product of the derivatives. And so we question that by putting a question mark there. And is this true? And it's very, very easy to show that this is not true. I'll put forth an example. So suppose we have the derivative of x squared times x cubed. And we're asking, does that equal the derivative of x squared times the derivative of x cubed? What I suggest you do is pause this video when I'm finished speaking and see whether or not you think this is true. I don't think it takes a lot of work to understand that this is not a true statement. So welcome back. I hope you were able to convince yourself that that is not a true statement. In other words, the derivative of a product is not the product of the derivatives. So what is the product rule? Well, the proof of this is given in the book. I've also given it in class, or will give it in class. And the derivative of a product is simply the first times the derivative of the second plus the derivative of the first function times the second. And again, I would suggest that you pause this video at the conclusion of this little piece and go back up to the top up here and apply that rule to, say, this particular function, and convince yourself that the product rule does indeed work. So here's an example to show how the product rule works, and you may want to try to do this work yourself. In other words, pause the video right now, do the work yourself, and then see if you get the same result that I get. So the derivative of this product, here's the product, is the first times the derivative of the second plus the derivative of the first times the second. And that's all she writes about that particular problem. So now let's think about the quotient, and we'll talk about the quotient rule. And by now you should be suspicious enough to think that the derivative with respect to x of f of x over g of x is probably not equal to the derivative of f over the derivative of g. And you're right, it's not. And once again, this is a rule whose proof is given in the book and will happen in class, and I'll simply write it down now. So the derivative of a quotient is going to be this. Okay, now we do have a way to remember this. And the way to remember this, if we think of the, let me change my pen color. If we think of this as being the function on the bottom, which we'll call low, and this the function on the top, which we'll call high, then the quotient rule comes out to be low d high minus high d low all over low squared. So let me help you see that. Low d high minus high d low all over low squared. And whenever I use the quotient rule, I'm always saying to myself in the back of my mind, low d high minus high d low all over low squared. So let's look at using the quotient rule for this example, and I'll speak out loud now. So this is a quotient, so the derivative is low, this is what I'm saying to myself whenever I do a problem like this, low d high minus high d low all over low squared. Pretty simple. You do need to try to remember how that formula works. Once again, low d high minus high d low all over low squared. Now, we have shown that the derivative with respect to x of x to the n is equal to n times x to the n minus 1, but we've only shown that if x is a positive integer. So at this point we want to ask the question, what if x is a negative integer? What happens in that case? Luckily, the same rule works, and let me give you a proof of that. So let's let n be a negative integer, and we want to try to take the derivative with respect to x of x to the n. So our properties of exponents enable us to rewrite this as 1 over x to the minus n. Notice that minus n is a positive integer. And so I could use the quotient rule and the power rule to take the derivative of this. So it's going to be low d high minus high d low, which will be minus n times x to the minus n minus 1 all over low squared. And you should be able to simplify this and show that it's actually equal to just n times x to the n minus 1. Very simple algebra to show that that's true. So what that tells us is that the power rule works for all integers. So we see now that we can extend the power rule and write that the derivative with respect to x of x to the n is going to be n times x to the n minus 1, and that'll be true for any integer, not just positive integers. So that concludes our discussion today on all the different rules of differentiation. Notice now that with the quotient rule, we can not only take the derivative of any polynomial, but now we're able to take the derivative of any rational function. So we have yet to learn how to take the derivative of exponential functions, logarithmic functions, trigonometric functions, and inverse trig functions. So lots of fun yet to come. See you next time.